Ever wondered what an ant's eye or a grain of salt looks like up close? Regular microscopes can't show us the tiniest details. That's where the scanning electron microscope, or SEM, comes in. Instead of light, SEMs use a beam of electrons to reveal the hidden textures and structures of the microscopic world. Scientists use SEMs to study everything from cells and insects to metals and rocks, uncovering details invisible to light microscopes. The SEM gives us a 3D-like view of a sample's surface, showing texture, shape, and arrangement. By using electrons, which are much smaller than light waves, SEMs can magnify thousands of times more than regular microscopes. To work, SEMs need a vacuum, so electrons travel straight to the sample without bumping into air. This creates a clear path for electrons, letting us unlock the secrets of the tiny universe. At the top of the SEM is an electron gun, a heated tungsten wire that releases electrons. These electrons are accelerated and focused into a fine beam using powerful magnetic lenses, not glass. The beam is narrowed to less than a nanometer, allowing for ultra-high resolution. Scanning coils move the beam in a precise pattern across the sample, line by line, like reading a book. As the beam scans, it interacts with the sample's atoms, and a computer records the signals to build an image pixel by pixel. Scientists can adjust the beam's energy lower for surface details, higher to see deeper. This control lets researchers tailor the SEM to their needs, revealing surface textures or internal features. The result: stunning, detailed images of the microscopic world. When the electron beam hits the sample, it knocks loose different particles and rays. The two main signals are secondary electrons and backscattered electrons. Secondary electrons come from the sample's surface, revealing its shape and texture in 3D-like detail. Backscattered electrons bounce off heavier atoms, making those areas appear brighter, great for spotting different materials. Detectors collect these signals, creating images that show both structure and composition. The SEM can also detect X-rays emitted by the sample, each element producing a unique fingerprint. Using an EDX detector, scientists can map out which elements are present and where. This turns the SEM into a powerful tool for both imaging and chemical analysis. We don't just see the surface, we learn what it's made of. Before imaging, samples must be conductive so electrons don't build up and blur the image. Non-conductive samples, like plastics or plants, get a thin metal coating just a few nanometers thick to prevent charging. Once inside the SEM, secondary electron images reveal surface shape, while backscattered images show material composition. Bright spots in backscattered images mean heavier elements. Darker areas are lighter materials. By combining these images with EDX data, scientists get a complete picture structure, composition, and even elemental maps. SEMs help us understand everything from the roughness of a surface to the minerals in a rock. This technology is a cornerstone of modern science, letting us see and analyze the world at the tiniest scales. With SEM, the invisible becomes visible and understandable.